All right, great. Well, I am Jackson. Thank you guys for being here tonight. I'm the communications coordinator, and today we are lucky to have Dr. Nicholas Foukal with us. Let me put my piece on real fast. You'll get a chance to clap. You'll get a chance.
You can clap now, Joe.
You can clap. It's like a jazz concert.
Yeah,
Okay, I think we're good.
gotta figure this out.
Dr. Foukal is an assistant professor in the University of Georgia's Department of Marine Sciences, and he is a member of the faculty here at the Skidaway Institute. He earned his bachelor's degree in engineering sciences, modified with economics from Dartmouth College, his master's in oceanography from the University of Maine, and his PhD in earth and ocean sciences from Duke University. Prior to joining SkIO in 2024, Foukal was an assistant scientist at the Woods Hole Oceanographic Institution. He is a physical oceanographer interested in where, when, and how the ocean stores and transports the sea. Now you can clap. Please welcome Dr. Foukal. Okay, to start off, can you tell us what is the AMOC and why is it important?
Sure. So, okay, the AMOC is a bit of a mouthful. So it's the Atlantic Meridional Overturning Circulation. So Atlantic is just the Atlantic Ocean. That's pretty straightforward. Meridional just means north-south. So that's actually one of the most important parts of the AMOC is that it moves heat northwards in our climate system. Typically, it's pretty difficult to get flow, whether it's the ocean or the winds, to move north-south. And so this is the interesting part of the AMOC is that it moves heat north and south. Overturning just means that there's some sort of vertical restructuring of the water column, essentially. And in this case, basically what happens is the Gulf Stream waters, if I can go back, let's see, does this work? Gulf Stream waters that are probably pretty familiar to most people here go northwards, and they form this colder water. Essentially, they give off their heat to the atmosphere. When the water's cool, they become denser, and then they sink. And so that's the overturning component, and they return southwards. So right off the Savannah coastline here, well, it's pretty shallow for quite a while until you get to the continental shelf break. And then you get the Gulf Stream that's moving heat northwards. That's the surface layers. And then if you keep going offshore into the deep layers, you get a southward flow. So that's the sort of abyssal circulation or the depth intensified western intensified southward flow. So this overturning circulation moves a lot of heat northwards. It is the reason why you can live in London quite. Uh-oh. Let me try to reword that. Yeah. So it's the reason you can live in London quite easily. But if you look at the same latitude on the eastern side of Canada, it is quite cold. And so this is a redistribution of heat in our climate system. Our global society has essentially evolved around this system being in place. So any perturbations to that would cause pretty dramatic restructuring of the way we think of society, essentially around the ocean. The other thing I just want to mention here is that if you look at a map of surface circulation in the North Atlantic, the AMOC is actually not the first thing that will pop out off the page at you. It's actually essentially sort of a residual of what is called the gyre circulation. And so that's what's shown here. There's a subtropical gyre that moves clockwise, essentially down here. That's the Gulf Stream. About 90% of the Gulf Stream waters recirculate southwards, and then they come across into the Caribbean and go around in this gyre circulation. So that gyre circulation is about 10 times stronger than the AMOC, but it doesn't move as much heat northwards or across latitudes meridionally. It does do some of that, but not as much as the AMOC. And so, yeah, I think that it's not, the AMOC gets a lot of publicity and press because of its heat transport, but it's actually not as strong as some people might think it is otherwise.
Great. So what influence does the AMOC have on us here locally in Savannah? Does it have any influence on our fisheries or our weather patterns here or any of that?
So the number one control on local climate here is the Gulf Stream in terms of oceanographic controls on our climate. And as I just said, about 10% of the Gulf Stream is this AMOC circulation. So the AMOC kind of rides on top of the Gulf Stream and the subtropical gyre. And so if the AMOC were to change or the part that's responsible, the part of the AMOC that's responsible for local climate is a relatively minor effect here. If you look at other latitudes or other regions, like I said, in London or Reykjavik, or even in the equatorial regions, the AMOC has a big impact on the climate there. But locally, it's actually not all that big of an effect. Yeah, I'll stop there.
Yeah. Well, can you speak a little bit more? I mean, you brought it up already, but can you speak a little bit more about the impact that the AMOC has on the climate of different areas
Sure.
throughout the world? I mean, it's heightened in some regions, like you were saying, in many parts of Europe compared to its influence here in
Yep.
Savannah. So you can kind of talk about where it's most prominent and what that means.
Sure. So one of the biggest impacts that it has is that it brings heat towards Northern Europe. And this is a paper that just came out this year that sort of looked at the impacts of what an AMOC collapse would entail. So there's some hypotheses that the AMOC is potentially unstable and it could collapse. Some people say as soon as this year. I'm not in that camp, but that's certainly on the table. So this is the temperature sort of impact, and they're talking about 20 degrees C temperature impact on Northern Europe. And it's especially true in the winter months. So the winter months is when the ocean really gives off a lot of heat to the atmosphere around this region. And it keeps this area, especially around London and Reykjavik and Bergen, Norway is kind of the epicenter of this. It keeps that area pretty warm in the winter, relatively warm. And so if you look at this plot here, this is the monthly temperature trend, essentially. So going from January to December of these different cities. And this is the change when the AMOC collapses. So Bergen is this kind of cyan line, and they're predicting, according to this one paper, I'll just say it's one paper, a 35 degrees C change in February over Bergen. That's pretty noticeable. So, talk about global temperatures, we're talking about 1 to 2 degrees C warming globally. Certainly that's not true everywhere. It's going to be different patterns. But this AMOC collapse could have really very big impacts locally on Northern Europe. The other big impact that's not shown in this paper is that the heat transport, the way the ocean transports heat in the North Atlantic or in the Atlantic basin in general, is that it moves heat from the South Atlantic across the equator and into the North Atlantic. And that cross equatorial flow actually causes what's called the intertropical convergence zone. So this is in the atmosphere. There's this area where the flow tends to converge, and it causes a lot of rain right near the equator. And it's actually displaced slightly northward of the equator because of the AMOC. The AMOC moves heat northwards into the northern hemisphere, and it displaces this intertropical convergence zone into the northern hemisphere slightly by just a few degrees of latitude. And without that AMOC, if you took that AMOC away, that rain band essentially would move southwards towards the equator. And this is a region in the equatorial regions where you have very strong gradients between deserts, like for example, Saharan desert in Africa, and rainforests or jungles, very, very humid areas. And so if you displace that ITCZ, the intertropical convergence zone, you can cause places that were desert to be very, very wet very quickly. And that causes landslides, that causes mosquito-borne illnesses, that causes a lot of other things. And it also depletes the rainfall over the rainforests where there's a lot of biodiversity and other things that we really care about in terms of rainforests. So there's these two big effects, one in the Northern Europe and then another one near the equator. Interestingly, Savannah is kind of right in the middle. There's actually not a big impact. If you look at the temperature change over Savannah, it's almost zero. So if you subtract the AMOC, there's not a whole lot of change locally. I will just say that There's a lot of uncertainty with all of these projections, and so it's certainly not a experiment that I would like to go through as a Savannian. I don't want to rely on these model projections as our baseline that we're going to be okay here.
Yeah, so I mean, a lot of variety in the temperature changes, also depending on which study you're looking at. I mean, some of them are
Yep.
extreme, which with up to negative 35-degree temperature changes, which is crazy. We'll get back to that in a second, but I also wanted to ask what is contributing to the what is at least understood as a depleting AMOC system, right?
Mhm.
I don't know if it's going to fall apart
Sure.
if that changes, but what is contributing to that?
Yeah, so I guess that's a good point that we should differentiate between a decline in the AMOC, and that's actually, there's a pretty good consensus, scientific consensus right now. The AMOC is predicted to decline out to about 2100. And that's worrisome. It's not quite as worrisome as a collapse. So a collapse would occur over maybe, say, 10 years, and it would just go from its current state, which is about, we use these units of spheredrups, which is 1,000,000 cubic meters per second, just as a kind of baseline. The Amazon River is about a third of a spheredrup. So the AMOC transports about 15 spheredrups. So it's about 50 times stronger than the Amazon River. And if we essentially remove that or go from 15 spheredrups to 0 spheredrups, that would be a pretty, especially a pretty worrisome result, especially over the course of a couple 10 years or couple decades. So I guess there's this consensus about the decline. There is very little consensus over whether the AMOC would collapse over these shorter timescales. I do just want to reiterate that both of these scenarios are pretty worrisome. So declining AMOC will still have these effects. The only difference it would give humanity essentially a few more decades to respond to these changes. Potentially, if we could geoengineer our way out of that, that would maybe light a fire under us to do something. But the collapse scenario, we probably would not have time to change the way we've what we've already done to the ocean, essentially. There is one other point there, that there's a lot of momentum in the ocean. And so it's, once you see a change happening, it's very difficult to change that back. The ocean has a lot of heat content, it has a lot of thermal inertia, and trying to change a system that is this large and has this much flow is pretty difficult. And we are seemingly doing that already. So we want to avoid that if we can.
Right. And can you speak a little bit about what we or scientists think is causing these changes?
Yeah. Good point. Sorry. So the melting of the Greenland ice sheet is the one thing that everybody points to. So Greenland is conveniently essentially an ice cube sitting right in the middle of all of these important currents. So yeah, this is the right one. So there's a lot of ice that's locked up in Greenland right here. There's about 7.5 meters of sea level equivalent. So if all of Greenland were to melt, sea levels globally would rise by about 7.5 meters. So that just tells you how much ice is on Greenland. Greenland is a very small percentage of our area, surface area. Interestingly, this map is a pretty good map where it shows Greenland's pretty small, but if you look at a Mercator projection, all these flat maps, it makes Greenland look much bigger than it really is. It's actually quite small, well, relatively speaking, but it has a lot of ice on it. And so this fresh water that's coming off the Greenland ice sheet has the potential essentially to increase the stratification of the subpolar North Atlantic. So this area up here, this subpolar gyre, it's essentially there's a thermal component to the stratification. So the warm water wants to stay at the top, but there's also a salinity component. So the fresh water wants to stay at the top too. And so there's an idea that if you decrease the salinity by increasing the freshwater input, you could stratify this area and you would reduce the overturning, the exchange of water from surface waters to the deep waters. And that would cause this decline in the AMOC. The collapse scenario is going one step further, that there's actually a positive feedback in that the reason that there's overturning in the North Atlantic is because this area, the subpolar North Atlantic, is so salty. And that salty water, when it cools off, becomes very dense. That combination of being cold and salty is some of the densest waters. If you reduce the AMOC, then you reduce that salt transport. The salty water doesn't get into the subpolar North Atlantic as frequently. And so there's a potentially, it would freshen that region, which would further slow down the system. So there's a positive feedback loop. And we do have, from our IPCC models, we have coupled climate models where we can look at this, and we don't see a very strong positive feedback in those coupled climate models. That's good news. So that's why we don't project that there should be a collapse going out to 2100. That's a little bit different than that one paper I showed you. That one paper where the berg in Norway was decreasing by 35 degrees C did show a collapse. So there's some disagreement as to whether the AMOC would collapse in that scenario.
So there are some science fiction-y takes on the collapse of the AMOC. Like The Day After Tomorrow is one that comes to mind with the Empire State Building. Or no, it's the Statue of Liberty frozen over in New York.
I think also the Empire State Building too.
Okay, well, it'll probably all be,
Didn't differentiate between the two.
But that may not happen. But are any cities or government systems doing anything to prepare for the decline or the potential collapse?
Not really. So there's the closest that I've seen so far was that a group of 40 scientists got together and wrote a letter to the leaders of, I think it's 7 or 8 Nordic countries. So Iceland, Norway, Denmark, a few other ones. And they basically laid out the case for an AMOC collapse and said that governments should be doing something in response to this. I haven't seen any response from the government in terms of acting on this information. There was a lot of celebration and fanfare when this letter went out. But to be completely honest, I'm not sure what a country like Iceland would do in response to this. This would completely change their way of life. The Reykjavik is a pretty well-developed Western civilization or Western city. And it would be plunged into much, much colder than it's ever been in the past. So in terms of fisheries, and they're very dependent on fisheries there. I think it would be pretty dramatic. And short of the only other analog I can think of is the Pacific Islands that are getting flooded by sea level rise. And they're essentially trying to buy up land in Australia to relocate. So I don't really know. I don't know if Iceland's considering that, but it's pretty difficult to wrap your head around some of these impacts. 35 degrees C in the winter is a big change.
That's like 95 to 100 degrees Fahrenheit difference.
Yeah, something like that. So it's a big change.
Yeah. We can ask questions.
Oh, Svalbard. It's right up there. Yeah, pretty cold up there. Actually, no, I'm sorry. That's a data center. There's just some seed storage in Svalbard too, though. I'm trying to think. I think it's Svalbard. Yeah.
Here, I can turn it over to questions too, but I also wanted to, before we do turn it over to question and answer, I wanted to give you an opportunity because I'm curious about what questions pop into your mind when you, based on what you know and what you've researched about the AMOC. What are you thinking about? What are the questions that pop into your mind that may influence your current or future research?
Sure. Yeah. So, okay. The most concrete one is we're going out this summer to put moorings in on the East Greenland shelf right here. Basically, the idea there is that there is a hypothesis that the AMOC is actually more stable or more resilient to Greenland freshwater in this warming scenario, warming world that we're living in, than is currently understood. And the mechanism that's being tested there is that the East Greenland current, which is essentially this current right here, is in the past and actually is this year. Right now, it's ice covered in the winter, and more frequently in the more recent years, it's becoming ice, or the ice is retreated, and so it's uncovered from the sea ice. And the importance for that is that the East Greenland current is a very strong current, and it transports pretty warm water under the sea ice. And without that sea ice, it can give off its heat to the atmosphere, and that would further enhance this overturning circulation. So the title of that project is called ROVER. It stands for Resilient Overturning in a Warming Climate. But there are these ideas, these essentially negative feedbacks in our climate system that could potentially diminish some of these positive feedbacks, like this positive feedback of the salinity feedback that I just talked about. So that's one thing. We're putting moorings out there this summer. There's another project called OSNAP, which is Overturning in the Subpolar North Atlantic program, that's been measuring the overturning circulation using moorings since 2014. And we're trying to continue that time series out until 2030. And basically in that project, we're just trying to monitor the AMOC and provide as real-time data as we can. We don't, all these moorings that I'm talking about deploying in the ocean are subsurface, because we don't want to get hit by ships, and we don't want to get hit by ice, and there's a lot of things that happen at the surface that we try to avoid. And so we only collect the data every 2 years when we get the moorings back. So it's not real time in the sense that you can go out and look at what the real time conditions are, but it's a lot better than some of our long-term proxy records, which will only give you information over 10-year time periods. So those are the big projects. The other one that is pretty fascinating to me right now is that there's a lot of fresh water coming in from the Arctic through the Canadian Arctic archipelago. So that's these islands north of Canada. And those straits in that archipelago are very narrow and very difficult to model. And so we're trying to constrain how much fresh water is coming through there using as many moorings as we can. And so we just pulled some moorings out from Eastern Canada, where we think that a lot of that fresh water accumulates on the Labrador Shelf. And we're in the process of analyzing that data. And I'd like to get more involved in more projects in Baffin Bay and the Canadian Arctic archipelago.
Great. Well, I'm going to turn it over for questions now. I'm going to come around and give you this just so I can get the audio, if that's okay. One second.
You don't want me to go get this?
Yeah, go for
This is a very simple question. Why does the AMOC break off in that particular area of the ocean?
Mm-hmm.
Why is there one at all? Why does the Gulf Stream just keep happily circulating around, in a clockwise direction? What causes it to break off?
It's a very simple question, and it's not a very simple answer. So, so just as an example, there is something called the PMOC, which is the Pacific Meridional Overturning Circulation. In the current climate system, the PMOC is about 0, and the AMOC is relatively vigorous. So, but if you look at paleo, sort of going back in the really back, I think you have to go back about 20,000 years, even before actually, probably past 50,000 years. There were time periods when the PMOC was more active than it is right now. And so that gives you an idea of why there would be this, so in the Pacific, the Gulf Stream is not the Gulf Stream, it's called the Kuroshio, goes along Japan. There's still a western boundary current. Essentially all this warm water just circulates in what's called the Pacific subtropical gyre. And there is a Pacific subpolar gyre up here, but they're not very connected. And that's the difference. In the AMOC, there is this very strong connection, or relatively strong connection, between these gyres, and that connects the flow meridionally, or north-south. Okay, so the reason there's a couple of hypotheses. I wouldn't say any of them explain it in full, but one of the reasons that the AMOC is active right now is due to the orientation of the basin, essentially. So the Atlantic is much narrower and elongated meridionally, or north-south, than the Pacific. The Pacific has a much wider aspect ratio. And partially due to the shape of Brazil, which is not in this map. Essentially, the equatorial currents go northwards along the north coast of Brazil and push some of this water northwards. There's also a hypothesis that it's driven by the exchange of warm water from the Indian Ocean into the South Atlantic around South Africa, essentially. And that boundary essentially is further north or more equatorward than the South American boundary. South America extends further south than South Africa. So those are kind of the orientation ones. There's also the Atlantic is much saltier than the Pacific. And the reason for that is that this isthmus of Panama, essentially, that connects North America to South America is very narrow. And the atmosphere, the winds over this area go from east to west, and they pick up essentially a lot of fresh water gets evaporated over the North Atlantic, gets rained out over the Pacific, and there's this salt or freshwater transport essentially over this continent. And it doesn't exist at higher latitudes where the winds switch from easterly to westerly, essentially. So the Atlantic is constantly being depleted of fresh water, or the salinity increases. And so it's a much saltier basin. And if you, this is a little more in detail, if you look at the thermodynamics of ocean water, essentially when salt water cools off, it becomes very dense, whereas fresh water, it needs to cool off by a lot more to become dense. And so that overturning is not as vigorous in the Pacific.
In the annals of geologic time, has this ever happened before?
Yeah.
And did it contribute to the ice age that we had eons ago?
So ice ages, as opposed to day after tomorrow, which essentially imposed a ice age over New York City because of the AMOC collapse. So ice ages are not forced by AMOC variability. AMOC variability does respond to ice ages. And so the reason that this whole hypothesis came up, and I should have mentioned this earlier, is that as we came out of the last ice age about 15 to 10,000 years ago, there's very strong evidence that the AMOC did collapse over the course of decades, and it was very unstable. It went essentially through a few transitions in that period. It's called the Younger Dryas period. And there's another period about 8,000 years ago where it's less strong evidence, but there is some evidence that the AMOC might have collapsed during that period too. Now, the big difference between that period and now is that most of the Northern Hemisphere was still covered in ice, or the high latitude Northern Hemisphere was covered in ice. So it's quite different background climate state than we have right now. And that presence of ice gave a lot more fresh water that could actually cause these changes. And one of the biggest ideas or hypotheses, most promising hypotheses, was that there was a big lake that formed in the ice sheet over Canada as we were coming out of the last ice age. There was a dam, essentially an ice dam, that was holding that water on land, and then it eventually broke as we came out of the last ice age, and it dumped a lot of fresh water into the subpolar North Atlantic all at once, and that caused this big change. We don't have a system right now where we could create a lake like that. The only closest analog would be the Beaufort Gyre, where there is a lot of fresh water that's stored there. But we would have to see variability in the Beaufort Gyre that is beyond what we've seen in recent past. So we're not too concerned about that. And so the motivation for understanding these nonlinear sort of tipping points in our climate system from the paleo literature is important to understand, but we also have to understand that the climate was in a different state then. And we're not sure if the AMOC is as unstable now as it was 12,000 years ago.
Thank you. I'm wondering if, closer to home,
Sure.
whether or not Gray's Reef has any impact on what the temperatures happens to the temperatures of the water, and whether that would impact anything.
Good question. So I just moved here from Massachusetts, so I'm getting kind of briefed up on the local geography. Certainly it does. Gray's Reef is about 20 miles offshore. Yeah. Okay, so the Gulf Stream is essentially impinging on our shelf break, and sometimes it overflows onto the shelf break, and sometimes it stays further offshore. And I'm sure the structure of the continental shelf, which is Gray's Reef is part of that, has a big impact on that. And as it's built up and decreased over time, I'm sure it's controlled how much of that Gulf Stream water comes onto the shelf at some level. I will just classify that as a bit of speculative. The AMOC stuff I know more about, but I'm sure it does have an impact at some level, yes.
Is there an impact to our weather, like hurricane, rainfall, that type of thing, with the deterioration of AMOC?
Yeah, so that's a great question, and so the temperature impact locally is something that we don't necessarily expect to see. I'm actually going to try to show a slide too. So let's see if I can do this. So this is the same study that I showed before. So basically this is North America. So they averaged, in this model, they averaged the conditions over this box. That's North America. That's what they say is all of North America. And they say, okay, the red line is the temperature from January to December of this area before an AMOC collapse. And then the blue is after the AMOC collapse. There's not much of a change. And that's kind of what we saw before. Europe, big change. There's, we have this before AMOC collapse and then after AMOC collapse. The precipitation is in the background. So those bars that you can barely see in the background, that's the change in precipitation. And there actually is some change in precipitation. And it's not huge. It's not like, we would all of a sudden be in a different climate state than we are now. But it is appreciable. And there's a known mechanism that would describe why the precipitation would change. Basically, if the ocean is not transporting this heat northwards, there's an idea that's called Bjerknes compensation, that the atmosphere would essentially pick up the slack and it would transport that heat northwards. That's essentially what happens in the southern hemisphere, is that there's not as much of a overturning in the southern hemisphere transporting heat towards the poles, but the atmosphere does a lot of that work. And the way that the atmosphere moves heat northwards or poleward is through storms. So the idea is that if the atmosphere became more needed to transport more heat northwards, it would activate more storms, which is, of course, something that we should be worried about here. I would say that's more of a hypothesis level. So I wouldn't put as much confidence in it. The temperature changes like over Northern Europe, that's kind of first order impacts. The shift in the ITCZ that I talked about, that's also pretty first order impact, pretty wide consensus. This other kind of second order or knock-on effects of how the ocean and atmosphere system would respond and over what timescales they would respond. How long does the AMOC have to collapse for the atmosphere to pick up the slack? It's pretty unclear. So I don't have as much confidence in those results, but I think there is a mechanism by which you would change the storms and the climate. And essentially, there's also this idea that just the jet stream is weakening essentially because the equator to pole temperature gradient is changing. And that we've seen changes in our variability of climate over Northern America just from that. So I think it's something that we should pay attention to, but it's a little bit less clear to me if that's something that I would expect out of an AMOC collapse.
Hi, thank you so much for your presentation. I was wondering how the decrease or collapse of the AMOC would affect migrating populations like whales and turtles and animals like that.
That's beyond my scope, but okay. So I just came from Woods Hole. One of my colleagues there was basically trying to reconstruct sea surface temperature in this area off Iceland back into the 16th or 17th century using whaling logbooks. And so basically those whalers knew how to find whales pretty well. And that's kind of true about oceanography in general. There's all sorts of fun stories about people finding seamounts where they didn't realize they were there. And then fishermen have been there for decades at least. They knew where those seamounts were way before scientists did. So I guess the point I'm going for is that the whales, and I guess from that paper that I was just talking about, they could see pretty large patterns at what's called the AMO, the Atlantic Multidecadal Oscillation. So they can see this sort of 60-year periodicity in the sea surface temperature around Iceland. A lot of people have speculated as to whether that is connected to the AMOC. It probably is, but it's really hard to connect those two right now. So if the AMOC is what's driving the AMO, this sea surface temperature of the North Atlantic, then I'm sure that's going to have impacts on the biology. Which ones are going to win out? I don't know. That's you have to ask a biologist. Yeah.
Probably got time for another 2 questions if we have them.
Let me ask one more.
Sure.
Yep, since the ice in the polar regions are melting dramatically, I'm doing work on the lost snows of the Alps and the impact of climate change on the snow cover in the Alps and that impact on the glaciers. So if we're seeing the results of global warming making it warmer in the Alps and warmer in Greenland, why would we worry about losing, the AMOC because it's going to get warmer anyway?
Yeah, well, the size of those two signals is not comparable. So the global warming is, 1 or 2 degrees C. Certainly locally, there can be larger changes. The Arctic, for example, is warming about 4 times faster than anywhere else. But I struggle a little bit relying just on this one study that I've been pointing to, but it has the nicest figures, so it's easy to communicate. But so whether I agree that it's going to be 35 degrees C colder in Bergen or not, I probably don't agree with that. But I think it just goes to show how big some of these signals are, whether it's maybe 10 degrees. That's still huge compared to the global warming signal. So skiing in the Alps might be good in a few years if the AMOC collapses. But that's a very, yeah, don't quote me on that one. So there would be these competing effects over Northern Europe. Elsewhere where we don't see big changes, like North America, for example, big changes from AMOC collapse, then certainly global warming signal would be the bigger signal. I guess that's as much as I can speculate on that. Yep.
All right, well, thank you to Dr. Foukal.